Audio.
I need to get
Okay,
shared.
yep, now I can put you. Oh, okay, go ahead.
Yeah, hello everyone. So it's we're very happy to host the visit Professor Anupam Chattophadyay from the National University of Singapore to visit us today. So just give a short introduction about today's speaker. Anupam received his bachelor degree from Chattophadyay University, India, and master from Alari, Switzerland, and PhD from RWTH Aachen in 2002 and 2008, respectively. Since September 2014, he is with the College of Computing and Data Science, NTU, basically National Technical University of Singapore, as associate professor with TANU from August 19. His research interests include emerging technology, electronic design automation, or EDA, system design topics intersecting between the cybersecurity and AI. And I see he's now also doing a lot of quantum stuff, which we're talk about today. His senior member of IEEE and ACM received a JSPS visiting fellowship, which I believe from Japan, right? And also was IEEE Council of CEDA distinguished lecturer. I think I was a couple of years ago. So also for the distinguished lecture, and his research work have been published in many IEEE ACM transactions, Nature Science Scientific Report, Critical Review, and also led several spin-offs and technology transfer in the domain of EDA, IoT, and cyber security. So let's welcome Anupam to give a talk today. Thank you.
Thank you, Iran, for introducing. Good afternoon, everyone. It's my first time being in Duke, a very nice campus. You're showing me around the chapel and the grounds, very pleasant weather. So there is a proverb in our native Indian languages which says that you shouldn't try selling a needle to a blacksmith. And this is what I'm almost trying to do now, sitting with the co-founders of the quantum computing companies and one of the experts in VLSI and low power design, Iran, whom I have been following his research for many years. But still the world is brave and researchers tend to be brave, and where angels dare fools rush in. I will just share my opinions on what we are finding and seeing right now around the world of quantum computing. To give a big background on what we are active in our research group in NTU. So I primarily focus on design automations and systems, but I keep a tab on what's happening in the world of algorithms and technology. And no matter what you are actually working on in your independent research agenda, you will find yourself in some of these areas, so that either we are working on core algorithms or in core technologies. And I have been fortunate to get my glimpse of what world was like in the pre-wireless era, looked into the wireless receivers during my PhDs, then followed up with the cryptography. Naturally, when the world got connected, everyone becomes so cautious about privacy and security. So you have to bring crypto to that. Then numerical linear algebra with its repercussions in ML and AI and bioinformatics. Then at the same time, there were evolutions of technology with CMOS in-memory computing, quantum computing, more things are coming on our way. So primarily people are trying to bridge this, that we have something in the mathematical abstraction going down to the world of physics or biology. And what we do here is on the background, trying to play around with architectures and algorithms in order to connect these things. I have been working on SoCs, ASIC, coarse-grained reconfigurable architectures, processors, made some design automation flows for each of them to connect this. So that's the background, and where we stumbled upon, there is a interesting thing like quantum computing, and we should take a note on what's happening in this. We cannot ignore it. So the first part of the talk is where I look into quantum computing and what our perception was, why we should do it, what's the important takeaways, and what we contributed in the design automation part. So this is how we perceived it, that there are some quantum computers from Intel, IonQ, PsiQuantum, which we call as universal. They are exposing different logic gates in quantum world for us to play around with. They are similar to general purpose processors. We can write any quantum algorithms on those. There are quantum computers like what D-Wave is marketing. They are akin to an ASIC, solving some very hard optimization problem by doing quantum annealing. There are lots of debates on whether they are actually showing quantumness or not, if there is a relevant speed up over a classical algorithm or not, but they are persisting. So these are the two domains. We mostly focus on the universal quantum computers because that's a more fun playground to deal with. And there, I think the most important question in the quantum world right now is, do we have an advantage or not? In the earlier times, we were talking about quantum supremacy, we talked quantum advantage, but can we establish for a practical application if it's there or not? And this is where the algorithm they're coming up with. And they say, okay, we have the computational complexity hierarchy, and there are some problems which fall into the dotted line called BQP, bounded error quantum polynomial time. And they have identified certain problems which belongs to BQP outside P. The most important of that we know of contributed by Peter Shor on factorization algorithm. And beyond that, if you go to the quantum algorithm zoo, there are a bunch of algorithms which tell that there are polynomial speed up, super polynomial speed up, quadratic speed up, exponential speed ups. But if we are talking about this speed up with the practical considerations, then this is what some people are arguing. I would call them as quantum skeptics. They say, okay, you might have great speed up, but that's not useful unless you are putting it into entire system. And then you are getting limitations from simple IO bandwidth like we have in our SoCs. And you have classical quantum computer, you may have hybrid quantum computer. And this bandwidth can affect things like HHL algorithm, which is the workhorse for many people claiming quantum machine learning. So that means if we take a very practical and skeptic view, we can actually throw away a bunch of quantum algorithms which are not affecting our day-to-day life anymore. But there are some things which are affecting, and most prominently Shor's algorithm. And what's the big effect of that is that it's going to disrupt a lot of security protocols. So this is a study in 2019. It has been since refined, including some estimates from ours, which tells that if you look into the crypto systems, there are symmetric key cryptography and asymmetric or public key cryptography. The public key cryptography, which sits under every security protocol between two untrusted parties, can be actually broken in a matter of hours if you have a powerful enough general purpose quantum computer. And that's something we cannot ignore. We can ignore quantum machine learning, we can ignore quantum database search, but this we cannot. This is not a good use case, I would say, but this is an inevitable and practical use case. If nothing, people will keep on driving just to see this particular doomsday scenario that we have a quantum computer attacking and breaking public key cryptography. So many people keep arguing that, okay, you need millions of quantum or so-called qubits or logic gates. This may not be practical. This may not be achievable. We will have noise build-up that you cannot correct. But engineers are actually trying to solve this problem, and there are very, very encouraging results on that, including Neven trying to promote something called Neven's law, akin to Moore's law in semiconductors, saying we will have more and more qubits that we can put in a superposition state. We can have more gates that can be crammed in. So this is actually well supported by IBM, who has a very audacious and ambitious roadmap, which they are fulfilling on year to year, saying, okay, in a few years' time in 2026, we actually may see 1 million qubits. And if we are in the domain of 1 million qubits, we might very well put RSA and SEC in trouble. So we cannot ignore this is happening. So with this, we started looking into, actually, even before that, I started looking into quantum computing as a platform, because I got curious in what's happening in that as a design automation engineer. So for you who have not studied this in depth, this is just the basic, that in a quantum world, we have something called a qubit, which is analog of classical bit in that domain. Different technologies can realize qubits. A qubit is represented as a basis state in block sphere, which is nothing but a superposition of 0 and 1 happening in this phenomenon. You can also get it into multiple levels. Instead of qubit, you can have q tricked or even qdit with the superposition state. This qubit, they can be operated by some transformations where you have an initial state, apply the gate pulses to get a final transform state. This transformation is what we know as our gates in the quantum world. Some of these gates, they have an analog in the classical world, like a CNOT gate between two qubits. What you see as lines here is nothing but an XOR operation, that you are having two qubits and they perform XOR to get you a resulting qubit. These operations can also be represented in a matrix formation, where you have an input state being transformed over a matrix operation to get a resulting state. Some of these gates, they cannot be represented in classical format, like you have a phase rotation gate, a Hadamard gate, or a T gate, but they are the building blocks that we need when we are trying to realize the transformations. So this is something that initially got me curious, that if I'm having a simple algorithm, like I want to do a multiplication and I want to do it in the quantum world, how do I map my multiplication onto this set of gates? This is the mapping that we have been doing all the time when we do classical logic synthesis with NAND and OR operation. But we can do the same thing in the quantum world, brings us a new set of challenges. The first thing that we need to know is what are the universal gate set. Like in classical world, in quantum, we have universal gates. And here one set of universal gate is called Clifford plus T gate set. Clifford group contains Hadamard, CNOT, and S gate. In addition to that, we have a T gate that makes it universal. And we are particularly interested in this gate set right now because they have very efficient fault-tolerant implementation in several quantum technologies. So like we had in the CMOS in 1950s and 60s, there were contending technologies on how to realize transistors and so on. We have the same in quantum. But since quantum computing itself is very, very noisy, we have to make sure that we are doing fault tolerance. Early results actually came from Peter Shor, who showed that quantum error correcting codes are practical. So this error correcting code together with these gates could be realized efficiently onto some quantum technologies. So that's where we have from our starting point. This gets us to the interesting juncture where people started building bigger and bigger quantum computers, but not big enough to do full-blown error correction or not big enough to do something like factorization on large-scale integers. But this was an interesting juncture where we are sitting now. We say, okay, we don't do error correction. We let the quantum qubits and operations still be noisy, but can we make something meaningful out of it? And this kind of quantum computer, they call as NISQ, Noisy Intermediate Scale Quantum Computer, a term coined by John Preskill, a physicist, who said, can we use NISQ to demonstrate some realistic thing, like some quantum advantage over classical? So this is the primary challenge. Can we find a high impact application, like a portfolio optimization, weather prediction, machine learning, that can already be achieved by small, noisy quantum computers? So this gets back to the system designers and design automation people, because if you are developing an algorithm, and if I want to accommodate it in a noisy intermediate scale quantum computers, then I have to figure out how to do the mapping in an efficient manner. That I may have a quantum machine learning, but I'm going to give you only 20 qubits, not more than that. Or I'm going to give you a gate depth of 50 gates, Beyond that, the noise will be too much. I cannot handle. So how do I cram this into this small constraints? So this is where I started getting into the problem of quantum computers, designing low depth quantum circuits, synthesis and mapping with small number of qubits and gates, following certain constraints that come from the quantum technologies. And for us, the main driving application as of now is the domain called quantum cryptanalysis, that we try to use quantum computer to break codes. So what did we do in design automation? I will give some glimpse of our works and try to just chart the evolution of this domain. So there are already commercial quantum computers which we can access over cloud. So that means if you write your own tool, you can integrate with IBM Qiskit, you can integrate with Stack. These are open source tools. Write a quantum circuit for a target quantum platform using those design automation flows, and then actually test it experimentally that you are doing it right or not. So what's happening in the quantum algorithm in the design automation? Very similar to the compilation flow in a classical world where we go from a C to a binary, or very similar to the Verilog to the GDS2 mapping in case of logic synthesis. We describe a quantum algorithm in a quantum programming language, then we perform a compilation which maps onto a target platform. Inside the compilation, we have multiple flows where we start borrowing from the knowledge we had in the high-level compilation, in the logic synthesis. Why we have certain representations like that? Because let's say we want to realize Shor's factorization algorithm. Within the factorization algorithm, there is a computation-intensive block like modular exponentiation. So we can implement modular exponentiation using Verilog code. We all know Verilog code. Then we convert the Verilog code in form of quantum logic gates, where quantum gates like Clifford gate and T gates. After mapping all these things, we finally get the mapping that we can send to a cloud, and there are acceptable formats for the cloud-based quantum computers. You can send there and you can get your results on the mapping. Inside the logic synthesis for quantum circuits, so this is something that is very core to our discipline in the EDA. You can start from a Boolean logic like a truth table or a binary decision diagram. You can convert into an equivalent quantum diagram. And here the quantum diagram looks like you have the qubits, which are the lines, and then you have the gates, which are operate over multiple lines, the qubits. There are some very nice works that have been done in this domain, like zero ancilla synthesis. You don't bring in additional intermediate variables or additional qubits when you synthesize. You synthesize for very specific circuits like modular exponentiation. Then it was shown in a very nice paper by Peter Schellinger that you can get quantum circuits for specific circuits with the T depth of 1. Now, T gate is one of the costly gates when I'm mapping the Clifford plus T family. So I want to minimize the T depth. So you can have a T depth 1 mapping. And this particular diagram shows that if you have a binary decision diagram, BDD, then you can have a 1-to-1 mapping from a BDD structure onto a quantum circuit. So this could be scaled up. There are logic synthesis flows that we experimented with, where we looked into the structural logic representations like AND inverter graph, which is scalable, and also functional logic representations like truth tables and binary decision diagram. So they have their trade-offs. The structural flows are scalable, but that doesn't lead you to the optimal results easily. You have to work hard on the heuristics. Truth table and BDD is very good for getting the optimal representation, but doesn't scale well. So what we did in one particular work is where we looked into a structural description, picked up the part where it's hurting most, the depth is very high, or there are too many gates. Then we optimized those parts using BDD representation, stitched it back to the structural representation. So you can have a hybrid logic synthesis flow like that. In more recent times, people are experimenting with LUT-based synthesis, XOR and graph-based synthesis, and you can go into that. So this is the logic synthesis part, but of course, that's not all, because you have to go into the technology mapping. And in technology mapping, there are new kinds of constraints which are offered by quantum computers. which we didn't see in the classical. So we have to play around the circuit in order to resolve this constraint. One such constraint is that if you have distant qubits and if you apply gates onto that, then either the gates are costlier or it will build up more noise. So you rather avoid it. So how do I convert distant gates local? I can apply swap gates, where two different qubits which are far away, I swap them to bring them closer. And then I apply the gate, I swap them back to their old positions. On the other hand, if I'm adding this kind of swap gates, I am actually increasing my depth and gate count of the circuit. So the question is, how do I do a constraint optimization, minimizing the swap insertion, at the same time, making every gate operate locally? So there are nice heuristics that we worked on this. And then we also looked into the same problem when I don't have a simple arrangement of qubit, but in the case of, let's say, an IBM machine, we have a mesh-like arrangement here. So this is my target platform, where the nearest neighbor definition is changing based on the qubits. There are many, many qubits which are nearest neighbor. So this problem of mapping a quantum circuit onto this kind of platforms become a graph to graph mapping, where I have to achieve the nearest neighbor constraint in my original source graph to satisfy the constraints of the target graph. So this problem we could do with an ILP formulation with depth optimality result. There are other technology constraints that came up apart from 1D and 2D topologies, is that the qubits, they might have difference in their behavior. Some qubits are less noisy, some are more noisy. Some gates are not so good with fidelity, some gates are more. It's a very quirky world. To fix this kind of things, we have to first do a calibration over the entire quantum platform, telling these are good qubits, these are bad qubits. These gates will perform well, these gates will not perform well. Can put together all of this in a mapping flow that we call as a Mukut flow, where we started with an input quantum circuit, looked into the final quantum circuit, then took into account the topology graph, did a subgraph extraction to map certain qubits onto this, followed by qubit configuration, nearest neighbor compliance, and fidelity aware mapping. So this kind of flows are now becoming prevalent, and almost any commercial tool flow, including IBM's or Amazon, they have these steps to achieve low depth, less number of qubits, and technology compliance. So this, once these are put into the existing flows, the kind of problem that we started getting interest in, what about specific circuits that we're talking about? And that is one of our PhD students looked into, and she basically experimented with quantum arithmetic. With all possible adders was one of her first tasks. And she said, okay, adders are already known. Everyone is doing adders. But we figured out that there is a lot of choices of adders in the quantum world that are not yet explored. So we created a Harris diagram like we have for classical adders, where the trade-offs are T count, T depth, and qubit count. Then you can map different adders into this mapping, pick up the one that fits your requirement. The choice of the adders starts from the prefix tree, propagation and generation, modular or non-modular, in place, out of place. More and more such choices are getting important. They show you these trade-offs are possible. Why these adders are important? Because we are eventually going to deal with, again, with source factorization, which needs modular exponentiation, that needs multiplication, that needs adder. The same building block. If I have a good adder, I will go with a good factorization algorithm all the way, and I will break RSA faster. So that's the idea. So far so good, but the students in our lab, they got a little bit bored with simulation and experiments in the cloud and so on. They say, we want to see the real quantum computer. And luckily at Singapore, we do have one. And we went to see this ion trap quantum computer. We were demonstrated some functionalities with this, with quantum machine learning. With the 1 qubit, you can do a technology called re-uploading that shows a 2-class classification or multi-class classification. Once the demonstration was over, we said, okay, we can hack it. And that was a real quantum computer on which we basically put in malware. Of course, the quantum computer does not have an OS or software stack. So the malware is operating in the target CPU. This is very much same as any critical resource. Like if I say I'm having a malware running on a smart grid, it's not running on the grid's electrical operations. It's running on the microcontrollers controlling the grid. So quantum computer still has a very, very weak spot with the target CPU. So we designed a custom malware, sent it as a link. The user clicked the link. In many cases, the user do click the link. Then the link was activating a manipulation of the scripts which is controlling the FPGA and DDS, sending all the pulses to the ion trap. So once we could manipulate, we could show that by increasing the noise and modification of the amplitude, we could reduce the accuracy of the quantum machine learning that they are running. So this was one of our, let's say, sweet revenge against quantum computer that's poised to break the classical world. We could use a classical technique going all the way to the quantum world. So this is ongoing work because we have some results right now on how we can create adversarial attack on the quantum machine learning. But note that this quantum machine learning that is realized here on the ion trap, these are published already. These are still not giving us any promise of quantum advantage. It just shows that with 1 qubit, you can do classification. We can do such classification much, much cheaper with the classical computing. But this is what's happening in the quantum world and our experiments. That brings me to the second part of the talk, where we are looking exclusively into post-quantum cryptography. What's the post-quantum cryptography? If we look back into public key cryptography, this is the foundation for any kind of communication between untrusted parties for 50 years. Since the time of RSA and ECC, you do net banking, online gaming, everything. You have these two classic peers, Bob and Alice, wants to sign something digitally, wants to exchange key. Then they are going to rely on some public key cryptography algorithm to set up a session key. After that, the symmetric key takes over and you have the channel to continue the communication. So PKC or public key cryptography we use today are based on the results from Rives Shamir Edelman, 1977, elliptic cryptography by Neil Koblitz in 1983. They are not broken because they rely on the hardness of prime factorization and discrete logarithmic problem. And that has been going on all till we figured out, or Peter Shor figured out, that there is a polynomial time algorithm running on a quantum computer that can break this. So this became a serious concern because quantum computers started scaling, and then NIST in US, they took leadership together with some other organization. In Europe, there are other organizations telling that we have to figure out what to do when this year Y2K comes, Y2Q, years to quantum. So they proposed some standardization for post-quantum cryptography in 2016. And around that time, we started looking into the candidates. With time, more and more candidates got eliminated. With 2024, a few weeks ago, the first standard for post-quantum cryptography got released. So we are looking towards an era where we will move from the current cryptography to the new set of cryptography. So in the world of cryptography, this is not something absolutely new. We moved from DES to AES in 99, 2000. We moved from SHA-1 to SHA-2 in more recent past. But those were symmetric cryptography algorithms. With public key, we are actually exposing the entire communication network. And even more, this is something we got used to over 50 years, that this will not be broken. This is really secure. We have a lot of database, a lot of protocols which are built on top of this. So what do the standards say? That we have several algorithms based on lattice-based cryptography, hash-based cryptography, code-based cryptography, recommended in US, recommended in Germany, on key exchange or digital signature. So these are right now in the focus of the cybersecurity world or the cryptographic world. There are other algorithms which are being studied in independent PQC standardization in China, in India, in Korea that we are aware of, but they are still primarily based on this hardness of these problems. So the first thing that we looked into is when the post-quantum cryptographic algorithms are going to be implemented, they will still be implemented on a classical computer. So your mobile will have a security protocol running to contact with your banking server. And this security protocol will have post-quantum cryptography. So your mobile is vulnerable to something that we call as side channel analysis or side channel attack. So this is a phenomenon that was again discovered at the beginning of in the 2001. So PQC standardization committee took it very seriously. They said, okay, of course you will resist quantum attacks, but you will also have to resist implementation level attacks. So whenever we are doing an implementation of an algorithm, it's leaving a lot of information side channel, which can be sometimes a very, very fine grained, like the transistors making noise inside your computers will leave some footprint that you can capture and you can perform an attack based on that. It's called acoustic cryptanalysis. There are, of course, much more prominent leakages, like the timing of accessing the cache in the software, or like the power consumption, like the electromagnetic wave that's being emanated. All this lives with enough information so that you can recover the secret key, you can recover the message. So we need to understand the post-quantum crypto algorithms that we are devising for the quantum computing attacks. Are they resistant against physical attacks or not? So this was one of our focus studies. And we figured it out that this is important for the quantum safe migration that we are trying to migrate. How does the migration works? That we have to build a lot of libraries which are side channel attack resistant for the different standards from NIST or BSI. These libraries will power security protocols like TLS, X3DH, which will again run certain security solutions like VPN, certification. Finally, facing the users in the application domain like automotive, IoT, consumer electronics. So basically the migration that's going to happen over next 1 or 2 decades, that will have repercussions against all of these layers. So knowingly or unknowingly, you will be affected. This is also visualized nicely in this chart where it shows that there is a system life cycle and a data shelf life. So if you are having a system that is going to be operational for 30, 40 years, then you must start migrating now, because before that shelf life expires, quantum computer will definitely be here. If you say, okay, my data just needs to be here for 2 years, you may ignore, because we think the consensus is quantum computer to break RSA might take longer than 2 years. But if it's taking longer from the system or data, like you are on the top right corner, then you should worry and start moving now. So we did a lot of work here on this particular topic, including efficient implementation, studying of physical attacks and so on. We built a set of libraries. I will just give a glimpse of a couple of attacks to end this seminar. The first attack that we did was on the timing vulnerability. So this is just the decryption part of the lattice-based cryptographic schemes like Kyber, where the decryption flow, it basically takes the cipher text and then it uses the private key followed by, again, some implementation or some input from the cipher text, which results into a particular value that's M dash, takes it all the way to the decoding, and then we get the final message. This is the decryption flow. In part of the decryption flow, we have to do a certain step, which is decompression of the coefficient from lower to higher modulus. So this decompression step, it actually calls this particular operation where you start with an encrypted M followed by certain summations where this ace, that's a secret key, that's exposed. What we found out is in the libraries of Kyber that is publicly available, this decryption operation internally calls a division instruction or IDIV, which has timing sensitivity. So if this IDIV operation has a particular quotient that is n less than 3329, it takes D clock cycle. If the quotient is more than 3329, it takes extra 20 clock cycles. So this is the part where we figured out, okay, we saw a link between the secret key S and the timing sensitivity of one of the assembly instruction in the decompression module. So this was the assembly snippet that you get for Intel x86-64 that was already being used by many software vendors in their Kyber implementation, in their migrated code. So we could easily link this particular weakness to recover the key, the secret key, by mounting a specific attack that we call as a chosen ciphertext attack. So we are selecting a ciphertext and we are repeatedly calling the decryption. The ciphertext is chosen such that it is invoking this particular difference between the timing. So this attack was then broadcasted to the people who have been using Kyber publicly. Many had to migrate back to the safer implementation. So this shows one of the perils of moving to the post-quantum world, that we are keeping ourselves safe from the quantum attacks, but we have to also ensure that our implementations are not vulnerable to simple attacks like this. So this is something we have to take into account during the entire migration journey. And this is something that we could ignore for many years because RSA and ECC are already on a solid foundation. They face side channel attacks as well, but those side channel attacks have been fixed by years of operation. Here we are discovering new attacks now. Every time we migrate, a new attack will come up. That could lead to something like a zero-day vulnerability or complete breaking of scheme. Something more ominous on that is that we can also show it's possible to do backdoor of the post-quantum cryptographic schemes. What is a backdoor? Is that if I give you an implementation, be it in a hardware or a software, you use that for running your encryption, your key generation, then you might leak some information that I can tap and I can garner your secret messages or secret key simply from that. So many people surmise that there is a backdoor that was already in RSA or certain implementation of PCC, which became a hot point of contention. We show that backdoors are also possible here. And to figure out whether the backdoor is not there on here, it is a very, very challenging problem. So how does the backdoor work? What a lot of lattice-based cryptographic schemes they are doing is they are trying to solve a learning with errors problem or LWE. The learning with errors is you are taking a matrix, you are multiplying with another vector, adding with a particular error value to get your T, where this particular instance is a noisy linear system. We are asking an attacker to solve. It can be shown that based on the simple error that we are introducing here, it becomes very, very hard for an attacker to break. We don't know of any efficient quantum algorithm even. So this is the basis on which LWE crypto systems are created. In Kyber KEM, what we see is that if we are trying to create an LWE instance with a public and private key, we give certain seeds, we have a generation procedure, multiply A with S, add with the error, we create a noisy linear system where A and T are public key, S is the secret key. We could slightly modify the same flow by adding one more source of error, what we call as our payload. The payload is where an attacker can insert a backdoor into the system. This backdoor can contain anything which is encrypted by the public key of the attacker. So the backdoors in backdoored information could only be recovered by the attacker with her or his private key. In this particular case, we simply send the values of the secret key into the payload. Then we could show that the key recovery is with 100% success rate with 1 million key exchanges. There was scope for adding even more information. I could add plain text and everything in the backdoor. It's simply leaking. Since this is adding an extra error, the LW instance is still considered valid. The LW instance can become invalid if the error is too much. Then the Kyber-like schemes, they result in something called decryption failure. So we could customize the error insertion such that decryption failure doesn't occur, and yet the backdoor is happening. So this calls for a very, very serious concern that if you are adopting PQC schemes and relying your secrecy on that basis. So with this, I would like to conclude the talk. To summarize, the capabilities of quantum computing is growing rapidly. We see very real impact in security. We don't know about others, but we are hopeful that there will be more algorithms coming up. it calls us to take careful steps into the quantum safe domain, which is supported by the growth of design automation, circuits, and system design. Need to keep balancing hype and reality. We invest too much in a particular research problem, identifying some benefit in quantum, but it may turn out to be a dead end. There is another very interesting research that's going on in this is to have quantum attacks on quantum safe cryptography. So to discover new quantum algorithms that can even break the post-quantum cryptography. And some of the early results started pouring in on that direction. So thank you for your attention. I would, of course, like to thank my students, collaborators, and funders for this research. Thank you.
Questions?
I have a question about the quantum sector. So when people are like, they have a reason quantum computers to run deeper like computers. So it's the cost of the computers.
Again,
So what is the cost of people to run the quantum applications? Like how long they need to reconfigure the circuit, to like redesign the circuit and do the activity cost for the circuit?
so that's a very different domain. If you say on the communications part, then there are approaches to do with the quantum key distribution.
No,
That's what you are
just for
referring
the
to?
first section.
I think it's about the reconfigurability. For example, you have a platform, you can run different applications. Each time you may want to customize the design. So I think he's asking how fast we're able to configure this power for different applications.
That is going to happen with the migration, that when we are going to the PQC, that there are definitely a lot of pitfalls there, and people are trying to come up with more hybrid schemes that they call it crypto agility, that they are still being based on RSA ECC. Using RSA ECC is one key generation, PQC as one key generation, and maybe even QKD as one key generation. Then you have a hybrid key combiner protocol, which balances out all of this to derive your key strength from. So in that case, you can argue that even if my PQC is broken by some side channel attack, I still have RSA to rescue. So the people who are doing the migration to post-quantum, they are advocating things like that, that I derive the key using a mixer or combiner protocol.
But the other part of your question about tape out. Yeah, so I think, so in quantum devices, you kind of tape out one device. And then the circuit is not in hardware. The circuit is basically in the call sequencing. Yeah, you send down electrical signals to or light signals to the device. But the tape out is once. The circuit reconfiguration is usually in compilation of software.
It's kind of like I have to say, but this time, each time you are configuring like the quantum gates.
Yeah.
So there's a proliferation on that, say, on a lot of QKD companies that are trying to advocate that we will achieve the security in the quantum world by using quantum key distribution. But the argument that we make is QKD by itself is not sufficient, because it just helps you to exchange the keys between 2 points. Of course, they have distance limitations and so on. They need repeater ports. But the QKD generator and QKD receiver, they themselves have to first establish the trust, which means someone needs to certify that this is a good sender, this is a good receiver. So you need a PQC-like protocol to build on top of this.
So, thanks for the presentation. And my question is regarding quantum DA. People often stop at quantum gates. People never go quantum gates or mapping, right? Device mapping, but people never go deep into, for example, whether or not it is possible to send out the parcels within a short period of time. People never consider the underlying engineering feasibility. So do you think that should be part of the EDA, or are there any research opportunity to incorporate the design challenges of a quantum computer below the complexity level into the overall.
So this is very much an open topic right now because there are so many languages and tool flows and platforms that are coming up. So there are some standards. If you look into, let's say, Qiskit, they are allowing you to write the quantum algorithm in different languages. And they also allow you to generate code which can run on different kinds of quantum computers. But there is always a possibility that there is a new technology which will come up saying, oh, we have to satisfy a particular constraint. Like your T gate is important, but maybe you should also care about the C naught gate. And suddenly we see that logic synthesis and technology mapping has to adjust to fit into that constraint. Yeah, so I would say if you look into company specific flows, they are very, very stable. You can take up something from Rigetti, you can take up something from even IonQ, you say, I want to realize my quantum algorithm on your device. They will offer a single straight flow. But that may not be the best thing that we researchers want, because we want things slightly open source, we want to customize, we want to have compatibility between different vendors, right? So this is what we want. And this is what's happening right now, that there are open source flows which are trying to bring in constraints from different platforms and bringing the uniqueness that different languages do offer.
And also, like, there are lots of quantum computers out there. Do you think there should be, open standard EDA, like open interface for, let's say, superconducting quantum computers? You have sort of constraint to describe the technology mapping constraint for that, and we have another, constraint for.
So we didn't try much on that because the things we ran on actual experimental devices are very small circuits that we were doing manually.
Oh,
Yeah. So we were, of course, working a lot on the EDA front, but then we figured out that more than EDA, what's the burning question right now is to find a killer application. So if I can tell that you will be able to break RSA with 1000 qubits instead of 1 million qubits, that will catapult the whole domain because people will take it way more seriously. Now, if I go to anyone and say, okay, I'm building a great EDA tool, the question comes back to me, okay, what the EDA tool is for? Where is the use? And then I say, okay, the use is because I will have 1 million qubits to break RSA. Then the reverse question is, it will take 10 years to get 1 million qubit. And I'm not a device guy, so I cannot fix 1 million qubits myself. The best thing that I can do is I can try mapping the adders and multipliers in such that instead of 1 million qubits, I need 1000 qubits.
Yeah, but that, well, just to say, I think that's very important work. And I thought your, the plot you have with your atom and kind of the, relative time, qubit number versus other published results is like super important. So if you can make, small changes on that plot, make huge differences in when these things happen.
I couldn't talk, thank you for the presentation, absolutely amazing. I have a question, I thought I heard the term, there was an attack on a quantum computer you did like in a lab in Singapore. I'm curious, could you like walk through that a little bit? What was the advantage to attacking the computer the way you did versus, I don't know, just turning power?
Well, so you attacked it from the CPU. So did you just sound like you changed the basically you changed the signals it was sending to the FPGA and therefore sending the wrong pulses to the ions?
There is some work on that, but again, I think that's not the most important question. So we are trying to ask the most important question, that's give me an application where we can defend the domain of quantum computing. So we did this kind of things in the past, like with in-memory computing, people were trying, with approximate computing, people were trying. So it's always good to have this big open challenge that everyone is trying to solve. There, I can tell you the problem that's happening is when we are building a quantum computer right now, it's like a hodgepodge mix of many devices around. So I looked into the ion trap machine. It's a big room with things that if you touch this and then the whole thing breaks down, right? So it's not something that's repeatable, replicable with a small form factor. People are trying. I mean, IBM has released their cloud-based quantum computer. But if I want something just to purchase from a store and install in my university, that's not happening soon. So one of the challenges there is if you see that so many wares coming out of a big quantum computer like IBM, is because the control is reading outside, and there is a lot of things which are inside a vacuum chamber, which is an ultra cold environment inside, right? And that's happening because the CMOS device or the FPGAs, whichever is controlling this, they are designed to operate in room temperature. So some people, they are trying to advocate that we should utilize cryogenic CMOS chips, cryogenic technology, which can operate in very low temperatures. And then we push everything together and make it a single integrated quantum computer. It's almost like you will have a quantum coprocessor in your system on chip. Long-term vision.
Right, and then just a quick follow-up, there was a discussion around like neighboring qubits. Were you talking about like photonic interconnects? Because Dr. Brown was sending some documentation on that recently. Just curious what you meant by that. Are you using swap gates? What's that? How were you connecting?
That is purely by applying the pulses, because when we see, because we are not bringing swap by pulling things here and there. So the swap is also a gate, that we have 2 qubits and then we are applying a pulse and they are swapping their position.
Last question is, that the quantum circuit for the adder, so, I don't know too much about this, so is the input and output is still the scalar, or do you have any assumption of the, like, how we transfer the scalar into some specific type, which can be further extended into the quantum adder? That means like the, you please work for more details about the, what is the quantum adder?
So in case of arithmetic or the adder circuit, so in the classical domain, people have optimized it for many, many years. But even now, you cannot tell this is an end problem. Even now, if you look into the top system or EDA conferences, you will find a new optimized adder, because people are playing around with the transistor layouts and they are doing something with a different sort. So one difference, for example, that we figured out is in classical, fan outs are free and okay to do. In quantum, you cannot do fan outs. Every fan out means you are adding more and more gates. Yeah. So you have to take it from the quantum standpoint and apply its benefits or constraints, whatever, to redesign the adder. And that's what we did. We looked into the classical adders, tried to map those one by one. So when you look into the adder, there is a prefix tree of large adders, right? So you have prefix tree from Coggestone, from Ladner-Fisher, from Brent Kuhn. So the question we were asking, which prefix tree is best in quantum? And we tried all of this, and then we got onto this different trade-off points in the quantum world.
So it's still a scalar adder.
And that's like the adder. Then we are now working on the multiplier, the divider, and exponentiation.
Just to add that early on, like one of the problems is that the adder has to be reversible with classical logic. Well, because it has to act on a superposition. And then it has to be like a unitary operator. Unitary operators have to be reversible. And so that was the problem. People would say, oh, I know a fast adder.
Yeah.
But then the fast adder is not reversible. And then there are no quantum instructions to implement it. And then anyway, that's why I love this plot, is that you now have this crazy trade-off between like additional scratch space and time, and like where to sit in that trade-off. It's not clear. Depends on all kinds of issues.
And another interesting thing is that if this is reversible, which basically means the input and output function is not the same as the scalar either in the classical circuit. Right? Because your circuit right now, they are all reversible. So which means right now what we are doing is we fix the problem. We say, okay, we want to use classic circuit and quantum circuit to put on scalar addition. But if but another way is like we can ask first what is the implement, what is the somehow like the best way for quantum perspective. Give me a circuit and I figure out what that function is, and I change the algorithm to that. So that function will not be a scalar addition. Okay.
Well, yeah, I see, no, your point's very interesting. I guess I know of some. So for example, you would love to do an AND gate. But an AND gate is also not reversible.
Yeah.
And so quantum mechanically, we use a Toffoli gate. And a Toffoli gate has a property that you, if 2 bits are 1, you flip a third bit. And then you can use that to be NAND, right? Sometimes making a Toffoli gate is hard. And then I won't get into this is too deep, but there's like a question of making sure the phases are right. But for some applications, you actually don't care about those phases. And so you can make something which is not a Toffoli, which classically still acts like an AND. Quantum mechanically is not exactly right, but for some applications it's faster. So I think that's the thing that comes to mind. Yeah.
Another question?
So there are no questions online? You had about 25 people online, there were?
Yeah.
Yeah. No
One reason because they're not so small, so people know it's not small. I'm sorry, because this is a very busy time for teaching.
Yes.
Yeah, so, but I don't want to walk back and forth with different buildings, but thank you so much, yeah.